its new future and arrangement. So many of you are probably already familiar with the JCMT. Maybe some of you are users of the JCMT. Well, I want to give an overview of what the JCMT is, what its instruments are, and then where we think it's going. And as Cheng Yuan has said, we're kind of in a new era of how we're funding and operating the JCMT. We're still working out some of those issues, and defining it. But you know, this is, I will say, you know, ASIAA is putting a lot of resources into the JCMT, and so it is your instrument to exploit and make the most use of. And we definitely want to hear from you about what you're interested in. So this is the most important thing to know about the JCMT. It is the largest single-dish sub-millimeter telescope in the world, which is a pretty remarkable thing to say about a telescope that is nearly 40 years old. But it is in fact the case. It has a 15-meter primary meter, excellent surface accuracy, wide field of view as a result of the multi-pixel camera that's involved. And I will say it has state-of-the-art instrumentation, which is also very old instrumentation. And that is a kind of a statement about how powerful these instruments were when they were first built. But we are looking ahead to a new generation of instruments. So for those of you who are not millimeter, sub-millimeter observers, you know, you might ask, why is the JCMT where it is? Why is it located on the summit of Mauna Kea in Hawaii, which is over 4,000 meters? It's because the primary source of opacity in the atmosphere is water vapor. And at 4,000 meters above sea level, we're above most of the water vapor. And in fact, the summit of Mauna Kea is one of the best sub-millimeter sites in the world, and so is uniquely a good location. And so this is the frequency coverage, and you see the atmospheric bands where we can observe, and you can see that we have instruments in many of those bands, going all the way up to 700 gigahertz. And because the weather is very good, we do frequently have time even at the highest frequencies. So this is a summary of the instruments that we have. So Namaka Nui, this is a Hawaiian name, and is actually the cryostat that holds 3 separate single pixel heterodyne receivers. They're each named after different Hawaiian fish, and they work in ALMA bands 3, 6, and 7. And we can also swap in a single pixel receiver that works in ALMA band 9. And we have done some tests with that, which I'll tell you about in a little bit. Which works up to 700 gigahertz. So this is actually a copy of the cryostat and the receivers the receiver suite that's available at the GLT in bands 6 and 7. And then the HARP instrument is a multi-pixel heterodyne camera. So it has 16 pixels, of which 12 are active. And it works in this band 7 range, and has a digital correlator back end associated with it. HARP is one of these very productive instruments that's been there for quite a long time, but was built so well when it was originally built that it remains unique and would be quite expensive to replace. Scuba 2 is the primary workhorse instrument of the JCMT. So this is a bolometer camera array. It actually has two separate cameras, or two separate pixel arrays, which one working at the 850 micron band and one working in the 450 micron band. And this is what gives JCMT a lot of sensitivity and a lot of wide field of view. We always like to say that the interior of the JCMT is the coldest point anywhere within thousands of miles of Mauna Kea, because of the cryogenic temperature that's needed, 72 millikelvin, in order to operate the Scuba 2 pixel arrays. We have two additional optical instruments that are associated with Scuba 2. One is a polarimeter, which is a rotating linear polarizer. And that has been heavily in use, and you'll see some results from that. And then the Fourier transform spectrometer, which has not been fully commissioned, but we have some new ideas about how we want to make use of it, and have been doing some commissioning of that so far. For those of you who are JCMT users, you might have known that Scuba 2 was out of service for over a year. It is a 15-year-old instrument, and it needed to have pretty significant repairs and maintenance work done. But back in April, those were completed. The telescope is back on the sky and is observing away. There is still one more major upgrade to the or refurbishment of the cryogenic system that needs to take place in order to sustain it for the longer period of time. Here you can see Scuba 2. It's really a massive instrument that's hanging off the backup structure of the telescope here. It's typically used in this kind of mapping mode, and we have what are so-called DAISY and PONG modes, which allow you to map out large areas of the sky, and that those modes are necessary in order to be able to remove the fluctuating atmospheric background that occurs. So it moves around quite quickly and allows you to differentiate between atmospheric variations, systematic errors in the chip itself, and then the sky signal. We get about a 15 arc second beam at 850 microns and a 7 arc second beam at 450 microns. This is one of the really spectacular recent results from Scuba 2. This is a map of Andromeda in the two different bands, 450 and 850 microns. And I just look at the scale of this, right? This is 2 degrees in scale here, and a real data reduction tour de force to be able to recover structures on scales as large as this, and also and at the same time down to pixels scales around 10 arc seconds, and so really a very impressive result. This is one of the polarization maps with the Pol 2 polarizer in concert with Scuba 2. This is the Orion region, and you can see this long filamentary structure, and then the electric field vectors, which map magnetic field structures in this star-forming region, and the so-called Bistro survey, of which there have been several iterations now, has explored a lot of different star-forming regions throughout the galaxy, and is giving kind of unprecedented and unique information on magnetic field structures in star-forming regions, and fills a kind of an interesting niche in between really large scales that Planck has surveyed and what you can do with ALMA and the SMA on much finer scales, and there's a lot of interesting physics there in star formation. This is just a summary of all the different Scuba 2 observations over a decade that were carried out. You can see it's observed huge chunks of the sky. So here is the HARP instrument and the AXIS back end. Both of these are over 2 decades old, and in particular, the digital back end we think is pretty ripe to upgrade to something with wider bandwidths and more capabilities. But a very efficient spectral line mapper looking at, for instance, CO 3-2 transition in galactic and extragalactic structures. Okay, so Namaka Nui, the heterodyne cryostat, you can see it here, and the cartridges are aligned here, and I think I've already said all of this information already. Okay, one slide on organization one slide on organization. So the JCMT was first commissioned in 1987. It was a project of the UK, Netherlands, and Canada. And in 2015, those partners pulled out and EAO took over. And so has been run by EAO for the past decade. Our current lease goes through 2030. EAO has had some rearrangement, but currently EAO is constituted by ASIAA and NARIT from Thailand. And then we have a number of other partners who participate, notably consortium of universities from the UK, many of whom have long associations going back to the beginnings of the JCMT, but partners in Canada, and then partners across East Asia who are contributing at different levels and making use of the observatory. Okay, just a few more science highlights. So the JCMT has, over the past decade, kind of worked in a mode of dividing time equally between PI programs and large programs, and large programs have typically been taking about 50% of the time, and many of them have been quite high impact. So this again is Bistro, and this is mapping magnetic fields in both 450 and 850 microns in the galactic center region, and the star is where Sagittarius star is located. And you can see this is a rich area. The magnetic field strengths that you infer from these kind of measurements are probably an important clue about how strong magnetic fields in the galactic center are important for regulating the star formation rate. There's a lot of dense gas in the galactic center, but the actual star formation rate is quite low, and we think that's in part because the magnetic fields inhibit them. This is a project that I've been involved in. So it's called the Transient Project, and it has been a study of young stars in star-forming regions within the galaxy, doing a monthly cadence of going back to these regions and looking for variability. And this was Doug Johnstone and Greg Hertzig have led this project, but the goal was really to focus on understanding the origins of variability and accretion onto young stars, and try to address that overall challenge. Lots of other interesting things have popped up. One of which is an exceedingly bright sub-millimeter flare from a young star. This is another one that shows this kind of secular variation, and there are a number of objects that show that kind of variation. And so this is a recent paper showing, the ALMA follow-up of this same object confirms the JCMT monitoring of this source. This is SCUBA 2 results looking at an extragalactic deep field and looking at a cluster, in fact. And there's a high redshift galaxy, a radio galaxy in here with a jet axis along this angle. And so the paper explores whether these other star-forming galaxies that are located in this cluster, whether they're influenced, or to what extent they're influenced by the powerful radio jet that's being ejected out of the center of this cluster. This is very much aligned with the kind of the long-term history of the JCMT, where sub-millimeter galaxies were first discovered and have long been characterized. And so this is kind of very much part of the kind of bread and butter of the history of the JCMT. This is the Malatang project, looking at dense gas tracers in nearby star-forming galaxies, and spatially resolving nearby galaxies, and then mapping a number of these kinds of tracers. And then, of course, the VLBI results. JCMT has been a central part of imaging both M87 and Sgr A as a part of the EHT. Here you see the polarized maps of both of these sources. I think nearly everybody here is pretty familiar with the EHT, but I think I would point out that my first involvement with the JCMT was in 2008, when we were doing one of the kind of proto-EHT tests. And I was at the other end. I was at the Karma telescope in California, and there was a group at the JCMT, and we had a 3 baseline interferometer experiment that detected Sgr and detected M87. And really kind of laid the groundwork for what the EHT has done. And so JCMT really has been central to all of that. And the location of the JCMT in Hawaii really makes it unique and powerful for continued VLBI activities. You can't, choose a different mountain, 100 miles away or 1,000 miles away and replace the use of Mauna Kea. It's in between North America and Asia, so it's quite useful. We get extremely long baselines from Hawaii to Europe, and Hawaii to the South Pole, and Hawaii to Greenland, and so it's really located in a quite important place. And because of the weather, we are a very reliable station in terms of being able to have good weather to carry things out. Just to point out, here's another pretty picture of the summit of Mauna Kea, and I won't go into all the details about the VLBI aspect. This is the sub-millimeter array. The JCMT is located right over here. We need the absolute best sites in the world to do this kind of science. And of course, the EHT results have been highly impactful. Black holes power active galactic nuclei. We're testing general relativity and the structure of compact objects over orders of magnitude in mass. And we're doing precision measurements of accretion and jet physics with these observations. And one of the things I worked a lot on as project scientist was trying to lay out what is the long-term science case for the EHT and establish that. And you see some of the questions that we pose here. You know, what is the origin of relativistic jets? How do jets launch? What causes flaring near supermassive black holes? How do we understand the magnetospheres and what can we learn from them? And then, of course, the really fundamental questions about space-time properties and black hole and compact object physics. So there's a really rich set of science to continue to carry out. I think in the interest of time, I'll skip over this. But so just to drive home what it is that we really, where we're really headed, right, is, we've taken individual images, but what we really want to be able to do is to make movies or to make time domain measurements, if you like. This is a somewhat old simulation of a formation of a relativistic jet from in M87. But one of the things you see is the persistence of the shadow feature. But you see there's all kinds of interesting dynamics that occur that are very informative about the accretion and jet formation physics. And we want to be able to see this and study it in detail. We also want to be able to remove all the things that are time variable and be able to isolate the things that are pure geometry and fundamental physics. So the EHT has proposed to do a monitoring campaign next year. We've proposed to ALMA, various groups have proposed for funding to support this, where we would do about 20 epochs of individual images of M87 over the course of 2 or 3 months, and begin to piece together this kind of time domain view. So a very exciting view, and JCMT is central to that. So I should point out, JCMT participates not just in the EHT, it also participates in the East Asia VLBI network, participates in the GMVA, and then there's a lot of kind of experimental and new directions technically in terms of VLBI that we're interested in exploring, and I'll talk about some of those in a moment. And one of the most interesting is to serve as a ground station for doing space VLBI. And so I'll come to that in a moment. Oh, that's my next slide. Okay, so the EHT has made images of 2 black holes. These are the 2 largest angular diameter black holes on the sky. How can we observe more? How can we see sharper features in those black holes? Well, we've reached the limits of the diameter of the Earth by having telescopes all around the Earth. We can either go to higher frequencies, or we can go into space and have longer baselines, or we can try to do both. And so this is, the Black Hole Explorer is a proposal that is being put together by some of our EHT collaborators and their colleagues to put a telescope in Earth orbit out to a few Earth radii, and this holds the promise of really revealing new sources and new physics in the sources we can already look at. It's technically extremely challenging, And one of the biggest limitations is this 3.4 meter diameter antenna. That's a very small antenna. And the success of this mission really relies on having very sensitive ground stations that can work with it. Now, the JCMT alone maybe is not sensitive enough, but the JCMT is co-located with the submillimeter array, and the two of them have about the same collecting area. And so we do think that the JCMT plus the SMA is potentially a very strong addition to the BECS ground array and the future of doing this kind of space VLBI. And again, because of the unique location, it's potentially a very important component of that project. Now, nobody knows if this particular project is going to succeed or any other space VLBI project, but it is very compelling, and it's had a lot of it has a lot of traction, and so it is an important thing to work towards. Now, the success of that experiment, in addition to having sensitive antennas, relies on the ability to observe more than one frequency at once. And the reason for this is because, as we go to higher frequencies, we get a sharper image, we get a higher angular resolution. But we also we also have greater distortions as a result of water vapor in the troposphere. And we have less sensitivity for the individual receivers and higher background noise. Observing with two antennas simultaneously, with two bands simultaneously, two frequency bands, allows us to detect the source at the lower frequency and then correct the atmospheric and any other instrumental fluctuations at the higher frequency, extending the integration time that we can have to observe these sources. And this is about, it's about extending the integration time from 1 second to 10 seconds, or 1 second to 100 or 1,000 seconds, and getting that, square root of time increase in sensitivity. So JCMT, with that tri-band receiver system that you saw, has the capability to do multiple bands at once, with the addition of some specialized optics. But this is one of the first tests done at millimeter wavelengths of this technique. And it's an experiment that involved both the SMA and the JCMT observing at two different frequency bands. So the JCMT observed at 86 gigahertz, the SMA at 215 gigahertz, with the IRAM telescope in Spain, which was observing at both frequencies simultaneously. And what you can see here is a demonstration that the interferometric phase between these on baselines to the JCMT and baselines to the SMA, appropriately scaled by frequency, that they track each other. Maybe not perfectly, but pretty well. And so that you do have the capability of extending the sensitivity and the coherence time of these kinds of observations. And this opens a whole new set of kinds of science that we can do with the JCMT and with other facilities. And in addition to being a stepping stone to more difficult experiments and to higher frequencies, there's also a huge range of science that can be done by having this kind of simultaneous dual band capability. This is just here's the Namakanui receiver opened up, or cryostat, and you can see the different receivers, the tri-band system. We've also been looking at making use of the a WSMA cryostat, which is a dual band system, and that potentially allows us both to could allow us both to do dual band VLBI experiments and also work simultaneously with the SMA as an interferometer. The next test that we've done, this was done last November, was the very first 690 gigahertz VLBI test. And you can see it was a 3-station experiment, ALMA, OPEX, and the JCMT. It was an experiment, and the end result is a little mixed, but that's not too surprising. So we have fringes from ALMA to OPEX. So long baseline interferometry, maybe not very long baseline interferometry. OPEX is, for those of you who don't know, is a kilometer or two away from the center of ALMA. We don't have long baseline fringes. We're trying to understand the origin of that, the nature why that didn't work. It could be there were some issues with the phasing of ALMA that we're still trying to understand. It could also just be a limitation of sensitivity, which is another argument for why this frequency phase transfer technique is quite important. I will say though, a very simple high frequency VLBI experiment, if you have the sensitivity that FPT could offer you, can be very powerful. I don't know about making an image from it, but you can make some very exact measurements. So this is just a simulation of a 4-station experiment. And what you see here, in particular, you see 1, 2, 3, 4 interferometric nulls that show up here. Now, it's a very simple model. The real thing will undoubtedly be more complex than that. But having that many nulls in your interferometric measurement will allow you to constrain the ring diameter and its properties very accurately in a way that in a way that to me is a bit surprising. It's actually quite powerful, and that I think a great deal of information could be extracted having that capability. Now, another way to get to these very high frequencies is to not just focus on the continuum sources, and it turns out that there are some extremely bright water maser transitions that occur in galactic objects, the atmospheres of evolved stars, AGB stars, and in star-forming regions. And they typically come from the same objects where 22 gigahertz, which is the kind of the most commonly studied water masers, are located. But look at this one, 3,000 Janskis. It is a really, really bright line. And in fact, so one of the challenges of doing this 690 gigahertz test is that we have to involve ALMA. It's very hard to get time on ALMA. It's very hard to do anything experimental with ALMA. For a source like this, we can observe jointly between OPEX and the JCMT, 2 single dish antennas, and have a pretty good chance of making a detection. In fact, the first VLBI detection at high frequencies. So this is a line at 658 gigahertz. There are also transitions at 321 gigahertz, so a more accessible band. And I think this is, making detections in this business is a big part of developing the capability to, do the fundamental physics that you ultimately want to get to. The other thing is there's all kinds of interesting science on its own that you can get in looking at these AGB stars and these star-forming regions. This is a map of SIO masers around an AGB star. But you see, the water masers have a similar kind of geometry. You see this kind of shell-like structure, and those structures actually pulse with the fundamental periods of these stars. And there's a great deal to learn. And it turns out, even with just a single baseline, if you can track these features over a few hours with Earth rotation synthesis, you can make a map, just a one baseline map of these kind of features, which is really cool. Okay, I want to talk a bit more about some of the other kind of future science cases for the JCMT and in submillimeter astronomy in general. So time domain science, many of you maybe were awake and watched the Rubin announcement earlier this week, or saw the images of these amazing wide field images. I need to update this slide, which I made a few months ago, with some of those images, right? And in the course of, just doing their preliminary verification, right, discovered thousands of asteroids, right? Thousands of new asteroids in just the commissioning work. The prediction is that LSST is going to generate 1 million transient events per night. 1 million. And, and many of them are going to be asteroids and space junk and things that are not detectable necessarily at millimeter wavelengths, but some of them will be. And this is really going to be a huge driver of what happens in astronomy and multi-wavelength astronomy. So I just want to walk through what I think some of the things are that we're going to see come, and what role submillimeter astronomy can play. So this is a very nice summary of extragalactic transients. You can see they span time scales that range from hours to months and out to years even. And they have supernova, gamma ray burst afterglows. There's a new kind of transient called an FBOT, fast blue optical transient. The first example of which is called the Holy Cow object, which is probably some kind of stellar wind shock that's occurring. There's a huge amount of theory around this, but I think the fundamental thing for all of these kind of explosive transient events is that a broadband spectrum in the radio and the millimeter is incredibly important for constraining the overall energetics of these explosive events. It's a so-called calorimeter model. And it's also very powerful for probing in the case where you might have stellar winds, the history of those winds, of what the circumstellar environment looks like. So you really get kind of unique and powerful information from this. Similarly, gravitational wave counterparts, we have had only one binary neutron star merger. Keep hoping that advanced LIGO will produce more. The first one, very faint in the radio, but it was detected there in the radio. As gravitational and multi-messenger astronomy advances, again, this multi-wavelength approach is really quite critical. And you can see how, different waveband observations probes different aspects of the physics in these sources. And so being able to study and monitor these sources is incredibly important. This is a nice result from the JCMT. This is a black hole X-ray binary outburst. Alex Teterenko, who was an EAO fellow, worked on this. This is the time scale here is 4.5 hours. and the source goes from basically undetectable to 7 Janskys in the course of less than 15 minutes. Really extremely variable activity and extremely bright. And all of that coincides with the launching of features in the jetted outflow. And so lots of interesting activity going on there, all the way up to the highest frequencies. AGN, lots of interesting variability that's going on there. This is an example that I really like of something I worked on for a long time and now others are working on, looking at the variability, the polarization of Sag star and variability. This is looking at the Stokes Q and U parameters and watching them over time, and they have this kind of circular motion that maybe is indicative of being able to measure in real time orbits of gas around the black hole or some other aspect of the dynamics. But really, really rich kind of information that can be found there. Potentially many other sources that could be studied this way. I mentioned this object earlier when I was talking about the transients project. This is a T-Tauri star observed with the JCMT that went from millijansky or less undetectable to half a Jansky in the course of an hour or so. There's a large magnetic eruption on a young star that's forming, and in fact, we think the most luminous stellar flare ever detected. Just really kind of staggering that the energy that's required to put something out. There's also all kinds of interesting periodic and variable emission that's detected among these objects. So actually that transients project was one of the first blind searches for variability in the millimeter regime. It was focused in star-forming regions, so not completely blind. The CMB experiments are, looking at extragalactic sky, and they have been blind searches for transients in that space, and they found a lot of AGN, and they've also found a lot of stars. There's just a lot going on with stars. So this is the main sequence, and you can see the range of different variable and transient stars that are detected in this space. And so we really expect a lot more of that to come. And then this is from a proposal to study one particular low mass star in detail from Rachel Austin. Again, we have stars that are hundreds of millijanskys, very bright, nearby, highly magnetized stars that can be studied on time scales of minutes to hours, and all of this really interesting physics and the millimeter observations probe a distinct region of that phase space, different from what you get at other wavelengths. So I think this is an area that's very ripe and for greater study. Okay, one more future science topic, which is intensity mapping. So this is my kind of go-to scheme of what is intensity mapping. So there are a lot of different ways to study the sky at large. If you have JWST or you have ALMA, what you typically do is you use some survey that identifies some really interesting objects, and then you use the high sensitivity but very narrow field of view of those telescopes to study a particular object in detail. But we actually know that a lot of the star-forming gas in the early universe and star formation material is not in the brightest of objects. It's in the ensemble of all the really small ones that are very hard to see. or find on their own. And so a telescope like LOFAR, low frequency telescope that can see really wide fields of view in neutral hydrogen, or a telescope like the JCMT, where we could be looking at molecular lines like CO or carbon plus from high redshift galaxies, and not focusing on individual ones, but focusing on a kind of a large scale detection. And how does this work in practice? How do we turn the JCMT into an intensity mapping machine? Well, we're relying on the same tools that are used for cosmic microwave background science, where instead of making a deep image at every different frequency, what we do is we construct a three-dimensional power spectrum. So angular dimensions on the sky, and then using the frequency axis to probe the redshift space. And we have access to the frequency axis if we're looking at specific lines that are dominating the spectrum, like carbon plus and like CO. And so we do that three-dimensional Fourier transform of the sky, and we can make a statistical characterization of the sky. And so we've done various pilot surveys, and there are a few dedicated projects to working on this. So the TIME project, which ASIAA has been a partner to, has worked on this. This is what the results look like, right? Is a wave number or a three-dimensional power spectrum unit and some power, and you explore what models can meet that and whether or not you can detect them. This is another way of looking at that kind of result. So you see the detected power and then the contributions that are expected from different lines, in this case different transitions of CO and transitions of carbon plus. And ultimately, this allows you to make an unbiased estimate of, say, the molecular hydrogen density over a large volume of space over the history of the universe, or the star formation rate over the history of the universe. So technically, what we want to do to achieve this is to use this four optic component called the Fourier transform spectrometer, which was built for the JCMT and to work with SCUBA 2, right? So SCUBA 2 is a camera with pixels, and the FTS splits the beam as it comes in, and then it self-interferes the beam, and you can vary the path length of that, which allows you to sample different delays. And this was built with the idea that you would sample a whole slew of those delays, and then you could just rebuild a whole spectrum. And so you could make a three-dimensional image cube. You could map, CO in a molecular cloud in the galaxy. It turns out, for a number of reasons, that's actually has not worked very well for this instrument working with SCUBA 2. But the requirements for intensity mapping are different, in that we don't need to scan over all of the possible delays. We can pick out a few delays that are of interest to us. We're looking at essentially blank sky in order to carry out these experiments. There are a number of simplifications. So right now we're testing this to see if this is a feasible mode for JCMT to operate in. And if it is, we might be able to do some pretty unique science in this space, something that you can't do at this point with any other instrument. Okay. I mentioned that our instruments are venerable, and so we are working on paths to upgrading the instruments for the JCMT. And so one of the things we're looking at is to replace Scuba 2 with a new camera that would have a capability, a survey speed that's about 10 times faster than what we can do currently with Scuba 2. So the MKIDS technology is really amazing. It's also about an order of magnitude less expensive than the bolometer technology. And we're currently looking at whether or not we can bring the Muscat instrument, which is currently deployed at the LMT, as a demonstrator and as a stepping stone to having an MKIDS camera on the JCMT. We're looking at upgrading HARP, wider band, more pixels. We're also looking at enhancing the digital back-end capability, getting rid of this 25-year-old digital correlator and replacing it with modern digital electronics, and then multi-banding the heterodyne system. So a lot going on there, and all of which are really kind of central to ensuring that the JCMT remains competitive into the future. Well, this is important too. We're an observatory in a place where there are a lot of people, and it's very important for us to carry out outreach and work with the community, and so we do. Okay, so this is my final slide. I think I've said all of these things, so I will stop now. Thank you.
And the floor is open for questions.
Keiichi.
So what I have for the future
Uh-huh.
for development, are there any
Well, so not yet, I think is the answer. VLBI is a very high priority for what we're doing. I think that, because of our funding arrangement here with ASIAA and the importance of VLBI here, I think VLBI is a pretty central activity, and most of the upgrades and activities related to VLBI are actually not very expensive relative to some of these other things. Scuba 2 is quite expensive to operate, uses a lot of electricity, we have to refill the helium dewar every month, and it's also just, it's showing its signs of its age. And given the importance of that kind of wide field imaging capability, finding the next generation instrument to replace Scuba 2 is a pretty critical technology. Something like a new digital back end, again, is not a really very expensive thing. So it's more about finding the opportunity to do any one of these things, finding partners who want to work on these things. We have a users meeting next week, and I want to, I'm relatively new to all of this, so I want to hear from the user community what they want from the telescope. I want to hear from all of you what you want from the telescope. What's compelling, and then we make a plan. Yeah, Britt.
Are there any plans to add FBT capability just on JCMT itself in the non-autonomy system?
Yeah. So absolutely, yeah. I mean, I think.
Because right now it's just SMA and JCMT.
Yeah. So I think this system of working with the SMA, it was a clever thing to do, but not optimal. And so, yeah, there are there's a design for optics that would involve a dichroic and allow you to feed two of the bands simultaneously. And so I would like to see, I think we need two designs for this, for the Beck's style thing, what we want is something like 86 and 345 or 86 and 230. I think to go to the highest frequencies, I think what we want is 230 and 690 simultaneously. And so, we need the dichroic systems that will enable that.
Thank you, Professor. My question is wondering about the priority for operating hub. Because I'm a frequency user for hub. But even for the available pixel now, for example, I'm using a frequency switch station. Even this specific for this phone, those available pixels still have some issues.
Uh-huh.
So I wonder about the plan to upgrade the hub. Will that be high priority or will they low?
I need to hear from more HARP users. HARP gets about 10% of the time on the telescope, which is just driven by proposal pressure. I know there have been proposals to develop new mixers that could go into HARP and would replace the broken ones. This kind of multi-pixel heterodyne camera is not the cost has not really gone down in terms of like other modes, like the MKids camera, because you're really still using fundamentally you're using the same kind of technology with lots of cryogenics and superconducting mixers, and which is why HARP still remains this powerful instrument, because to build something that is an order of magnitude bigger, 100 pixel camera like HARP, is probably a $10 million instrumentation project. That's, you need a really strong science case, and you need, continued effort over years to be able to achieve that. I think that's not very likely to happen. I think upgrades to it, to repairing broken pixels, maybe being able to get wider bandwidths out of it. I mean, how important to you would it be if we were able to get 8 gigahertz of bandwidth out of each pixel rather than 2 gigahertz?
For me, actually, I'm looking at light, so the bandwidth is not a critical issue for me. I really like sensitivity.
Uh-huh.
More pixel than the sensitivity.
Yeah. But you could look at multiple lines at once.
Yeah, that's true.
Yeah.
Because I'm looking at some tutoring molecules, so usually they are dense.
I see. Okay. Yeah. Right. Yeah.
So that's the reason I'm using frequency switch mode. But even for the available pixel, from the data I got, some pixel their frequency draw actually is different from the others. And my contact scientists they still need to spend some time to understand.
Yeah.
So even for those, it could be some issue.
Yeah. I can tell you that what I hear from the operators or the operation staff is that a HARP is the most difficult of the instruments to operate. The tuning it is difficult, and it has there's the most complexity to it. I do think if we could even if we could just replace the axis with a more modern digital back end, that might simplify at least some aspect of HARP, and we could get some more out, even if it didn't increase the bandwidth or anything of that sort. So yeah, thank you. That's useful to hear.
Well, there's no other questions. Let's thank Jeff again.